So yeah, today I'm going to be talking about spatial isolation implying zero knowledge even in a quantum world. And if you don't know what some of these terms mean, then I'll explain them kind of as we go along. So this is a joint work with Alessandro Chiesa, Tom Gurr, and Michael Forbes. Tom Gurr is actually now at Warwick. I forgot to update his affiliation. All right. So the thing that may be unfamiliar to you is this concept of zero knowledge. So what is zero knowledge? Well, let's say that we have a problem, a computational problem, such as is this graph three-colorable? Right? Can you color this graph with three colors so that no two adjacent vertices share a color? And this problem is known to be hard, NP hard. So maybe we want to delegate the computation of like working out whether this graph is three-colorable to some powerful computer in the cloud, right? So how can we get this computer to help us? Well, one thing that the computer could do is it could just say yes, right? Like it could check that the graph is three-colorable. It knows how to do this because it's very powerful. And then it could just tell us, yes, the answer is yes. The problem is that if we don't trust this computer, then this hasn't really told us anything, right? So the computer could say yes, and the graph could not be three-colorable. So what we ask for in addition is a proof. And the kind of typical proof, the NP proof of three-colorability is precisely a three-coloring. Right? So like the prover can write down the three-coloring, send it to me, I can check that the three-coloring is valid, and then I'm convinced that the graph was indeed three-colorable. So now zero knowledge is all about convincing me of this without telling me any additional information besides kind of what I asked for. Right? So what I wanted to know was, is the graph three-colorable? What I got was a three-coloring, which is a lot more information than just is the graph three-colorable. So what I kind of want is a way to, for the prover to convince me, but for the amount of information that I get to be the same as in this original protocol where the prover just said yes. Okay, and this is a concept due to Goldwasser, Macaulay, and Rakoff in the 80s. And it is known that if you make cryptographic assumptions, then you can get zero knowledge for NP, and in fact a bigger class called P-space, polynomial space computations. This has been known since the 90s. And it turns out that there's also a converse to this result. So if you have zero knowledge proofs for NP, then you can construct one-way functions from those, roughly. So this is kind of the whole picture for the single prover model. So what we're going to do is we're going to modify the model slightly, and we're going to look at multi-prover interactive proofs, which is what the model that Henry was talking about. So it turns out that once you have this model where kind of you have these two provers and they are kind of spatially separated and they can't talk to each other, then we know that you can actually achieve unconditional zero knowledge, right? So kind of in the classical world, you have this kind of spatial isolation, and this forces the strategies to be local. And you can show this is a classic result from the 80s, that you can obtain unconditional zero knowledge for NEXP. So this is non-deterministic exponential time computation. So this is even bigger than NP or P-space. And there are no cryptographic assumptions required. Okay, so as a complexity class inclusion, we write this as NEXP is contained in zero knowledge MIP. The problem is that as we all know, quantum mechanics means that spatial isolation doesn't imply this kind of local strategies. You can have strategies which use quantum entanglement. And the protocol that we use to show that NEXP is contained in zero knowledge MIP, as far as we know, it no longer works in this model. So let's just talk briefly about this model. So it's called MIP star. And here now the provers just share some state psi, and they prepare it to begin with, and then you talk to them. And they can't otherwise communicate with each other. And there is a question which Henry alluded to, which is how powerful is MIP star? And so we know since 2012 that this class MIP star contains NEXP, and so in particular it contains kind of the classical MIP. Note that this is not kind of trivial because in either direction, because on the one hand, the provers can use more cheating strategies. On the other hand, the provers can use more honest strategies. So it's not a priori clear which direction they should go in, and it's quite a lot of work to show that next is contained in MIP star. Okay. So now the question is kind of, can we extend this result about unconditional zero knowledge to protocols which are sound against entangled strategies, right? So is it the case that NEXP is contained in zero knowledge MIP star? Okay. So the answer is yes, as the talk title suggests. And you might be wondering kind of why this is hard to show, right? Because we had all of these components kind of already. They were, right, we have we know that NEXP is contained in MIP star. And we've known for a very long time that MIP is contained in, MIP is contained in zero knowledge MIP, right? So you can get zero knowledge for any MIP protocol for free. So why don't we just kind of, squish these things together and move the star down and move the zero knowledge up and then hope for the best. And the reason is that there's kind of a incompatibility of techniques, right? So the way that we know how to build MIP star protocols seems to rely somehow on algebra, or at least on error correcting codes. Whereas the way that we build zero knowledge, or this BGKW zero knowledge protocols, they're kind of more combinatorial in character, and they don't really, fit together. And so there are kind of two things you could do, right? You could either change the IV12 result to be more combinatorial to somehow fit with the BGKW result, or you could change the BGKW result to be more algebraic. And we do this second thing. So we kind of reprove this MIP contained in zero knowledge, NEXP contained in zero knowledge MIP in a more algebraically friendly way, and that enables us to use the results that we get from Ito Vidic in 2012 to show the inclusion that we want. All right. So how does the theorem go? So the proof is in 2 steps. So the first thing that you do is we show what's called a lifting lemma. So the idea is we start with some proof system in some weird model that's kind of has nothing really to do with quantum or anything at all. In fact, it only has one prover in it. And we show that you can take any proof system in this weird model and you can lift it to a proof system in the MIP star model. And in particular, this transformation preserves zero knowledge. So if the thing that you started with was zero knowledge, then what you get out is also zero knowledge and sound. Okay, and then the second part is to construct a zero knowledge proof system in this weird model that we need to kind of produce this, to use this lifting lemma. So I will explain kind of mostly the thing on the right, because the stuff on the left is more or less kind of it's taken from work by Tama and Ito Vidic and Anand Natarajan, and kind of just presented in this way. So just briefly, kind of how do we construct the lifting lemma? So the idea is that you start with something called a PCP, and you can lift it to an MIP star protocol. So this is something that is due to Ito and Vidic. And so what is a PCP? Well, a PCP is like a proof string, and it's a very long proof string, but the way that I check it is I only need to look at a few a few places, like maybe constantly many places in the string. And here, all of my machines are classical, right? So I just have I have this proof. It's available to me as the verifier. I can like query it probabilistically, but nothing quantum is happening here. And this is kind of the way that you obtain this NEXP contained in MIP star result. So you start with this lifting lemma and you apply it to an existing PCP construction, and this is what you get. Okay, so In order to prove our result, we're going to need to generalize this a little bit. So we can't just rely on PCPs. We have to rely on something slightly more general, which is called an interactive PCP. So an interactive PCP is just a PCP followed by a standard interaction. So you just you get a PCP, you can query it, and then you can talk to the prover, and then you can query the PCP again if you want to, this kind of thing. So it turns out that the techniques that were developed by Ito and Vidic can also be applied to this interactive PCP without too much difficulty. So far, so good. We've come up with ways to construct like MIP star protocols from these kind of information theoretic, like non-quantum protocols that we understand fairly well. The problem is that we haven't talked about zero knowledge. And the reason is that this lifting lemma as is doesn't preserve zero knowledge. So we need to restrict our model slightly in order to get this, this zero knowledge property. And the restriction is going to be that we need to place a restriction on the form of the PCP oracle. So what we define is a thing called a low-degree interactive PCP. And this is something where the PCP oracle is a multivariate low-degree polynomial. So like you can't put anything else in there. It has to be just one multivariate low-degree polynomial. And the reason that this works is essentially because in the other lifting lemmas, the problem with the reason you weren't getting zero knowledge is because you had to take your PCP or the PCP oracle, and you had to low degree extend it. You had to like make it into a low degree polynomial, and this breaks zero knowledge. So the requirement that kind of it's already in that form means that if you have zero knowledge here, you don't have to do the zero knowledge breaking step. And so you can carry the zero knowledge through to the final protocol. Okay, so how does the lifting lemma work? Well, so we start with this, this low degree test from Natarajan and Vidic, where, so this is a point versus plane low degree test. And this is to kind of constrain the provers to behave like a low degree polynomial. So what do you do? Well, the verifier is going to ask one prover for a point in the evaluation of the low degree polynomial, and he's going to ask the other prover for a plane, like the evaluation of a plane. And the provers just kind of write these down, and they send them as messages to the verifier. And what this guarantees is essentially that the provers can only really use their entanglement to choose a random low degree polynomial and then answer accordingly. Right? So we've kind of constrained what the provers are able to do with their entanglement if they succeed at this test. So this happens with probability half or whatever, some constant probability. With probability, with the rest of the probability, you do what's called interactive PCP emulation. So this is where you actually use the proof system that we constructed before. So we take our low degree interactive PCP, and what we're going to do, firstly, we do a query reduction so that there's only one query that the verifier makes to the PCP. This can be done generically. And then we essentially implement this thing using the two provers. So one of the provers is just going to be the interactive bit, and one of the provers is going to be the query bit, right? So clearly the interactive prover, he can tell that it's not like he's in a different game. But prover B actually doesn't know which game he's in, which means that he has to kind of answer in the same way as he would have answered if we were testing him. So he has to answer according to some low degree polynomial that has been drawn. And so this essentially means that we can assume that the prover, like the provers have agreed on a low degree polynomial, and then we can query them according to that. Okay. Yeah, so this is so like he's getting like a point query, which is distributed in the same way as in the low degree test. And so he must be behaving in the same way. In particular, he must just be using his entanglement to choose a low-degree polynomial and then answer accordingly. Okay. So that's the lifting lemma. So now I'm going to talk about algebraic zero knowledge. So this is kind of the second part. This is how do you get this interactive PCP thing that you transform into a MIP star protocol. So the problem is essentially that you need to construct this proof system which has strong constraints on what the oracle can look like, and you need to do so in a way that provides you with some notion of zero knowledge. So kind of a fundamental component of every zero knowledge protocol is a commitment scheme, and ours is no different. So we have a commitment scheme in this model, but it has to be kind of an algebraic flavored commitment scheme, because what we have, like the oracle that we have, needs to be a low degree polynomial. So how do you commit to a value using a polynomial? So let's say that the prover has some polynomial in mind that he wants to commit to. He's going to commit to it. And so this is kind of the general framework, rather, of a polynomial commitment scheme. This is what one looks like, and then we're going to construct one. So the prover is going to commit to this polynomial Q that he's got in his head. And then what you want is you want to be able to decommit to this polynomial at a particular evaluation point. Right? So he has this polynomial Q in his head that contains a lot of information, and I want it to be fixed. And I want to be able to decommit to individual evaluations of this polynomial, right? So the verifier can say, I would like show me the value of Q at X, and I get Q of X. And I want to ensure two properties. So firstly, the hiding property. So this says that if the verifier doesn't ask about Y, then he should not learn Q of Y. Right? So he should only learn the value that he asked for and nothing else. And then there's a binding property, which is that the commit phase somehow fixes Q. Right? So there is a Q in the prover's head that is fixed during the commit phase, and whatever the verifier says in the decommit phase corresponds to this polynomial Q. Okay. So let's look at a very simple case. Let's say that this polynomial Q has no variables. It's just a constant polynomial. Right? It's just a value beta in some finite field F. So the goal is you want to commit to this message, which is a field element, in a hiding and binding way. And we're going to look at this in this low-degree IPCP model. So the commit phase is just going to be a polynomial, some multivariate polynomial. And the property of this polynomial that means that it's a commitment to beta is that it's sum over some product set in F to the M. So there's a subset of the field H, and you look at all points inside of H to the M, you sum the value of P over all of these points, and you get beta, right? So this means that this oracle encodes beta in this way, in this highly redundant way, but it encodes beta, and it's unambiguously encodes beta. Then how do we decommit? Well, so what we have to check is that this equation holds, this sum over alpha and H to the M P of alpha equals beta, and this is a problem of summing over a low-degree polynomial, and we know how to do this. This is the sum check protocol. So for those of you who are not familiar with it, it's an interactive protocol. So this blue part is just a standard interaction. It's an interactive protocol for showing that some polynomial sums to something over a product set. So this is something that's very commonly used in interactive proofs in PCPs and all over the place. And this is how we will do the decommitment. So the soundness of this protocol ensures that you can't decommit to anything besides the beta that is encoded by this summation. Okay. So let's talk about hiding. So the intuitive idea behind hiding is that we've kind of hidden beta by making it a sum of a bunch of stuff. And if there's, like, if you think about what would happen if I didn't have this low degree extension, if I just had, like, took this set h to the m and I just gave you that, right? I want you to compute the sum over everything in h to the m and tell me it, right? You cannot learn any information about this sum unless you query every single point in the cube, right? Because if you fail to query even one point in the cube, then the sum will be whatever you computed so far plus that one point, right? The sum is still randomly distributed. So some complication arises because you don't actually just get this cube, right? You don't get this h to the m. You get a low degree extension, so you get a bunch more information about h, right? I tell you a bunch of these, like I tell you the value of some polynomial whose evaluation is h that is kind of what I'm interested in h to the m. But all of these points have, you know, they're non-trivial linear combinations of stuff that's contained in h to the m. And the question is, you know, is it still hard to compute if I give you this oracle, right? So now you can you have this extra power of querying points in the low degree extension. Does this make the problem easier for you to solve? And this is a question, this has already been given a name. So in this Aronson-Vigdisson paper, it's called algebraic query complexity. So the idea is that you're trying to evaluate some Boolean function, and you're not just given access to the Boolean function, but you're also given access to its low degree extension. And this is kind of part of this algebraization framework. And the answer, surprisingly, is that it's no longer hard to compute in certain cases. So if the degree, if this d is small and the size of h, like this set h is just 0 and 1. So this h to the m is just the Boolean hypercube. And you take the multilinear extension of the function of the Boolean hypercube, then it turns out that you actually only need to query it in one place in order to learn this sum over the whole cube, right? So there's some point which is given by the querying it at the inverse of 2, and like if you query it there, then you can immediately find out what this sum is. So this would break the whole hiding property, right? Because now I could just look at this point and I could find beta. So what do? Well, it turns out that you can fix this problem just by taking the degree to be a little bit higher, right? So if I take my polynomial to be not the kind of unique extension, but something where the degree is roughly twice what it needs to be, then I can compute. Then I can show that computing this sum takes kind of as many queries as it would if you didn't have access to the low degree extension. So how do we show this? So there are a few different ways to show this, but the one I'll show you is like nice and interesting and visual. So it's a reduction from communication complexity. So communication complexity, you have Alice and you have Bob, and each of them has half of the input to a function, and you want to compute the value of this function, right? And so the problem that we will reduce from is called unique disjointness. So the unique disjointness, these two strings represent sets, right? So you want to find out whether the sets have no intersection, they are disjoint, or whether their intersection has size exactly 1, right? And we know that so this is all classical communication, by the way. So we know that you require at least n bits of, you have to exchange at least n bits, order n bits, in order to decide unique disjointness. So you essentially have to send your whole input. Okay. And so the idea, what you do is you suppose that kind of computing this sum, P of alpha, takes q queries, then from that you can construct a communication protocol for unique disjointness where the amount of communication is roughly the number of queries that you need to make to this function. So how do you do it? So the idea is that each, like Alice and Bob, will both compute individually the load-array extensions of their inputs, right? So they will take this this bit string, and they will map it onto this product set h to the m, and then they will find a load-array extension of this function. So this f of x, this like fx, is an embedding of the bit string into this space h to the m. Right? You're just kind of rewriting it. And then p of x is the unique low-degree polynomial, the polynomial of lowest degree that agrees with x agrees with fx on h to the m. So they individually compute these encodings. This requires no communication. They just like encoding their inputs themselves. And then the idea is that I can compute this polynomial p of x, which is the product of these two, like of px and py, the low-degree extensions of the inputs to each party. I can compute this polynomial just by having, say, Alice send to Bob p of x written, like the evaluation of p of x written somewhere, and then Bob can multiply that with his evaluation of py, and maybe send it back if I need to. Right, so now I have a way in like kind of log f bits to evaluate this polynomial px, which is the product of px of like p little x and p little y. Okay, so now if x and y are actually disjoint, this means that the if I multiply fx and fy and I evaluate that over the space h to the m, this is 0 because whenever there's a 0 in x and a 1 in y, then this becomes 0 and vice versa, right? So it's kind of, this is like taking the and of these two strings, and so if it's yes, then this should be 0, the bitwise and of these two strings. Which means that the load-array extension also has to evaluate to this because it matches, like this p matches this product oh sorry, that's a z, it should say x, fx times fy over this space. So this summation is 0, and if this is not the case, or if it's sorry, if x and y share some element, their intersection like is exactly 1, then this summation will be 1 because there'll be one point where x is 1 and y is 1, and so when I multiply them together, I'll get 1, and then everywhere else it's 0. And so this summation is 1, right? So now we've reduced the problem of determining whether these two strings are disjoint to checking whether this polynomial sums to 0 or 1 over the hypercube. And now the point is that I can query this polynomial by making by doing this kind of small amount of communication, this log f size communication, which means that the number of queries that I need to compute it, if it takes me q queries to p to compute this sum, then I obtain a communication protocol where the communication complexity is something like q log f, so O tilde of q. And so going the other way, since n is of size roughly h to the m, it must take h to the m queries to compute this summation. All right. So I have 1 minute left. So let me just say that what we showed so far is about committing to this like beta, and we actually need to commit to a whole polynomial, not just one element. And this is something that you can do essentially by having a polynomial which is over more variables, and then when you sum out some of the variables, what you get is a polynomial over fewer variables that is committed to. But I won't have time to talk about that, so I'll just skip to the open questions. I had a nice animation. There you go. Okay, so open questions. One big one is this protocol has a lot of rounds. So the number of rounds is kind of linear. It's linear in the instance size. So the question is, can you do this in logarithmic or constant number of rounds? Can you come up with kind of these lifting theorems for richer classes of protocols, maybe things that actually capture quantum computation, right? So here we're stuck because this protocol could only capture NEXP. Maybe there are protocols that you can lift which capture QMA-exp or something like that. And the final question is, this whole thing depended a lot on low-degree polynomials. And one of the things about low-degree polynomials is often when you use them, you're kind of using them because you want a tensor code, but it's kind of shorthand for writing tensor codes. Tensor codes are a little bit more complicated. So is it possible to generalize these results to use any tensor code or any locally decodable code? And that is all. Thank you very much.
Any questions? Are there any other classes lower than ZK MIP to put it in, or is that
Sorry?
any more restrictions so you put it in ZK? Is there anything smaller than that?
So the containment.
For the result,
like NEXP is NEXP contained in anything smaller than ZK MIP star. So ZK MIP star might be very, very powerful. So this is kind of related to what Henry was saying. So MIP star could contain languages that are undecidable even, and so kind of it would be interesting to see what is the what constraints you need to put on MIP star in order to make it really NEXP. I know there's some things like if you restrict the amount of entanglement the provers can use, I think that you also get NEXP, something like that. But yeah, there's no. I don't think there's any really stronger containment that I'm aware of.
Okay.
Yeah, it would. It's kind of an open question. This whether this is because it's possible even that it's tight, right? If it's the case that MIP star is equal to NEXP, then ZK MIP star is also equal to NEXP.
Mm-hmm.
Yeah.
Any other questions? Okay, so this ends this session. Let's thank Nick and Henry again.